So I'll just give you some demonstration. So I have a matrix. In general, again, we're back to the non-square context. So this time you see I'm looking at the matrix which is not necessarily square one. I gave you, and I look at my matrix again from the general perspective. So I give like names to the elements of that matrix. And I give you one example just to make a demonstration. So we have three concepts associated with this: transposed, adjoint, and I also put here inverse, which we know now already, but still I just put it on this slide because there are some properties which are interconnected with the other two. So transposed matrix, it's the one which, look at this. Do I have a definition of that? Oh. Somehow I don't have it. Okay, I'll just put it here. Transposed matrix, that's the one which is like normally denoted like this. And that's the matrix which is the, look at this, what kind of size this matrix has. It's the size nm, so it's the other side, like I swapped over this in the size of the matrix with the complex entries. And the content of this matrix, look at this, what the content of that matrix is. These are the elements of my matrix, but indexed the other way, kj. If I use this example, look what happens with the matrix. Transposed one, it's the one where rows becomes columns. Here's a row, here's a column. Here's a row, second one, here's a second column. And finally, the last row is the last row, and here's the last column. Adjoint matrix, again, I just realized I don't have any like a formal definition of that. I'll put it here. Adjoint matrix is denoted by asterisk as a superscript rather than T, capital, as a superscript. It's again a matrix of size like the transposed matrix. So it's a size nm. Generally, it's with the complex entries. The elements of that matrix, they are, look at this, they not only we swap the indices this time, but we also take complex conjugation. That's the difference between adjoint and transposed. Compare this. Here we swap the indices, so we replace rows with columns. Here we do the same thing, but extra, we complex conjugate the entries. So the result, for instance, if I do adjoint matrix for this one, the result of that will be this. It is like this one, look at this. It's almost identical to this, but these two i's, and that's the reason I chose the complex entries, they go complex conjugate. So they go negative I and they go negative I. And that's the way we define transposed matrix and adjoint matrix. I also, of course, put here the inverse of this matrix. You don't have to copy that. That's the inverse we computed with you 2 lectures ago. So that's why I chose this matrix. We computed this inverse before with this interesting method with the geometric progression approach. Now, these two concepts, or 3 concepts, including the inverse, in case the matrix is square, they have some properties. They are quite expectable. I'll just mention them, and I'll do one example where these properties are needed. Look at this. I put them together. For instance, if you transpose the sum of 2 matrices, this is the same as if you transpose each of them individually and add them up. Similarly goes for adjoint matrices. If you add 2 matrices and then take the adjoint, you can equally adjoint each of them individually and then add them up. There's no similar relation for the inverse, by the way. You can't take the inverse of the sum as the sum of the inverses. Don't do that. It's a very very obvious sign that you know very little about the matrices, and if anyone who's marking your test sees something like this, it will disappoint them a lot, and it will reflect. It will be like you will see reflection of that in the mark. So that's this. Nothing like this exists for matrices. However, if you look at the products, we have 3 identical products for the. I mean, when you look at the multiplication, there is a connection there is a connection with the transpose, adjoint, and inverse in this case. Pay attention that when you take the transpose of the product, this is the same as the product of the transposed, but in the opposite order. And because the matrix product is non-commutative, you can't alter that. You have to swap the order of the factors. The same goes true about the adjoint matrices. Again, you can split the adjoint to each of the matrices, but you have to change the order of the product. And the same stands true for the inverses. If you take the inverse of the product, this is the same as the inverse of each individual factor, but you have to flip the order of the factors. That's why I put this all three on the same slide, because properties are very similar to each other. What else I have? Double transposition obviously brings the same matrix back. Double adjoint obviously brings the same matrix back. And double inverse obviously brings the same matrix back. Good. There is a connection between these three properties with the determinant, and that's the connection which is expressed by these three identities. Determinant of the transposed matrix, the same as the determinant of the matrix itself. What do you think will happen with the adjoint? How the determinant of the adjoint will be connected with the determinant of the original matrix, given you know this now? Complex conjugate, yes. Because actually the transposition, the adjoint operation is like a transposition and then complex conjugate to every entry of the matrix. So that's how it is for the adjoint. What about the inverse? Well, this is actually a very, very difficult result. It's a subtle, deep result. In fact, these two, they're not so deep, but this one actually, it's a deep result. The determinant of the inverse is the inverse of the determinant. And that actually suggests one of the tests for the inverse, because right now, if you have a matrix, square matrix, the only test you have at your hands, if the question goes, determine whether the matrix, find out whether the matrix is invertible, whether it has an inverse, you have only one test. You have to row echelon it. You have to bring it to the row echelon form and see if every column is leading. This one gives you another test. You can compute the determinant and see if it is non-zero. It is like implicitly said here in this property. It says that the matrix is invertible. So the matrix has an inverse if and only if its determinant is non-zero. And like I told you before already, that when you have, for instance, 3 times 3 matrix, finding the determinant with the minor method via the row decomposition, it is quicker than the row echelon form. It's not only on my example. I had lots of classmates when I was a student. Anyone prefer this over the row echelon form? After some practice, you will realize it's quicker. I hope you will realize. So testing for the inverse, for instance, when you look at the 3 times 3, determinant approach is quicker than the row echelon form. Well, for some of us. But it's just another alternative. If you still prefer row echelon form, it's another alternative worth remembering. Right. Do I have more properties? I have a few. I have another 2 properties here. I'll practice on those and I'll let you go. It's a connection, for instance, a connection like this, which says if you invert a transposed matrix, this is the same if you transpose the inverse of that matrix. If you inverse the adjoint matrix, this is the same if you adjoin the inverse matrix. I call this property, I just mark this property with the asterisk, and I'll show you the proof of that. There are a few problems in the yellow book where you have to do some manipulations abstractly with the symbolically with the matrices. And the proof of this example is a very good demonstration of this technique. The other demonstration is in 2 or 3 handwritten solutions in chapter 4. It's here. I'll give you the proof, and that will be the end of the lecture. If I'm looking at the identity like this and I need to prove it, so I need to prove that the inverse to this matrix is given by this. The way to prove it is like this. I have to look at the identity like so. It's a question mark. And I claim that if I show this identity, this is equivalent to showing this. The reason for that is just a definition of the inverse. Remember, the inverse is a matrix. The inverse is a matrix with this property. The inverse is a matrix with a property like this. Any matrix which will make this happening, we call it an inverse. So look at this. If I prove this identity, this big matrix will make this happening for this A transpose. So this big matrix will be the inverse of A transpose. Now the proving of this one is here. Look at this, what I do. I take the left hand side. Now I use this property, this one, in the reverse order. So I'm looking at the product of 2 transposed. I'll make it the product of 1 transposed, like this. I took care of swapping the factors, although in this case it's not so important, but still I took care of that. Now the inner bit here, we know this is just the identity. So we're looking at the transposition of the identity. But transposition of the identity, remember the transposition effectively just a flipping matrix over the diagonal. Transposition of the identity is basically the identity itself. And that's how you prove this one. So the question mark would be gone.